Hello everyone, my name is Ritik Parajuli and in this video I am presenting my TSA coursework project implemented in Java. Uh, in this project I solved multiple questions related to data structures, dynamic programming, greedy algorithms, graph algorithms, recursions and multithreading. I also created two Java Swing GUI applications. Uh, as you can see in the left side, this is my project structure. Inside the src folder, I organized the work questions by question into question 1, question 2, question 3, question 4, question 5 and task 6. That has made this code easier to manage and explain. Now I will go through each part of the project one by one. So let's first go to first question. Is on max points on a line. The goal here is to find the maximum number of points that lie on the same straight line. My approach is based on checking each point as a starting point and calculating slopes with all other points. I use a hash map to count how many points share the same slope relative to the current point. This works because if multiple points have the same slope with respect to one point, then they are on the same line. The time complexity of each of this code is roughly n squared because for every point I compare it with the remaining points. Then I tested them. Then let's test the implementation with sample inputs and let's print the result as well. So here we're going to test it out. We're going to write back out src this question 1 x on line that. Okay, now sample out. As you can see, our our sample inputs and our result. So yeah. The program prints the maximum number of points on the same line. Now let's go to question no, the second one of our question number 1. Let's, this the second part of question 1 is the word break problem where I need to generate or all valid sentence from string using words from this dictionary. As you can see here, for this I use DFS with memorization. The DFS part explores possible word breaks recursively and memorization stores already solved substrings so that repeated work is avoided. Without memorization, the recursive calls would become too expensive. With memorization, the solution becomes much more practical. So the main idea is I try every possible prefix, check if it exists in the dictionary, and then recursively solve the remaining suffix. In the end, I return all valid sentences and combinations. uh, this also check our okay, this shows all valid sentence combination from using found from the string input string. The src slash question1 slash word break all to Java. Here q1 I use DFS with memorization to avoid repeated computation, and as you can see the result here. Now we are going to go to question number 2. Max path sum binary in maximum path in binary tree. You can see the code here. For question number 2, I implemented maximum path sum in a binary tree. Here the path can start and end at any nodes, so it is not limited to root to leaf. I used recursion and depth for search. For each node I calculated the maximum gain from the left subtree and the right subtree. If a subtree contributes a negative value, I ignore it by taking 0 instead, as you can see here. Then I compute the best path passing through the current node is node value plus left gain plus right gain, as you can see here. And I also keep a global variable to store the maximum path sum found so far. This way the algorithm visits each node once, so the time complexity is also 0. Now we are gonna test this out too. src to some binary tree Java. This prints the maximum path sum in the binary tree. And the recursion calculates the best path contribution from left to right, as you can see here. Now we are gonna go to question number 3, which is stock max profit transition. It is about stock buy and sell with the eight most key transitions. Question number 3 is the stock buy and sell problem with its most key transitions. For this I used dynamic programming. I created a DB table where rows represent the number of transactions and columns represent the days. Each cell stores the maximum profit that can be achieved up to that day using at most that many transactions. To optimize the transitions I used a running variable called max difference. This helps avoid checking all previous dates again and again. So instead of slower DB solution, this gives a more efficient O k times n solutions. I also included test cases and pretend the DB table so the logic can be understood smoothly. Mm, 3 top wait a minute. And this question uses dynamic programming. The output shows test cases and the final computed profit. Profit. It also prints the DB table for explanation, as you can see here. Now we're gonna go to smart grid allocator. Question number 4 is about smart energy allocation. In this problem, I had to distribute electricity to district while considering source capacity, time availability, cost per kilowatt, renewable performance, and a minus plus 10% flexibility on demand. I used a hybrid approach combining greedy strategy and dynamic programming. First, the greedy part shows available energy source by cost, so the cheap source is used first. This helps reduce total cost. Then the dynamic programming part is also used to choose district target allocations while staying within the allowed flexibility range. This helps the solution practical because it tries to satisfy demand as much as possible while respecting constraints. In the end, the program prints how the distribution, total delivered energy, total cost, renewable share, and whether diesel has to be used. This question is a good example of combining optimization and real-world constraints. So this prints by hour allocation result. this first. This is less. Uh, Sorry. This print hour by hour allocation result. It shows demand, delivered power, cost, renewable share, and diesel uses. The greedy part shows the cheapest available source first, as you can see here. Now we are going to go to tourist spot optimizer GUI. Now coming to question number 5, part A. This is a GUI based tourist itinerary planner built using Java Swing. The user can enter available time, maximum budget, interest tax, and start time. Based on those results, based on those inputs, the application generates an itinerary. I use two approaches here. One is heuristic based planner, and other is a brute force comparison. The heuristic approach is faster and makes decisions based on things like tech math, matching, travel time, and review. The brute force approach takes all possible valid combination for the smallest data set, so I can compare whether the heuristic result is close to the optimal result. The application also includes a coordinate path view where the chosen travel route is drawn visually. So this question demonstrates GUI deployment, optimization logic, and comparison between experiment and exact solutions. You can see here, you can find the code in my GitHub link. Let's test this also. The code can be found here. Now let's test. As you can see here, uh, here I enter the inputs to generate the itinerary. The app compares a steering result with the approved first result. The route is also shown visually in the coordinate path. See here. And now moving on to the weather collector app. It is an multi-thread weather data collector. It is also a Java Swing application. It fetches weather data for 5 cities and displays temperature, humidity, and pressure in a table. The main goal here is to compare subsequential execution and parallel execution. In the subsequential part, that city data is fetched one after another. In the parallel part, I use multiple threads, basically one task per city, so the requests happen concurrently. To keep the GUI safe, I update swing components using swing utilities that invoke later. The application also shows a latency comparison chart and a log area, so the user can clearly see the parallel execution is faster than the subsequential execution. The program demonstrates multi-threading, GUI programming, safe UI updates, and performance comparison. And let's go 5. Let's fetch the weather and see. This application compares subsequential and parallel weather fetching. The table shows the weather data for 5 cities. The chart below compares subsequential and parallel latency. The log area shows the execution details. Yes. Now let's move to safest path. Type 6 it is the safest path problem. Normally, the Zikra algorithm works with additive weights, but here the safety of a path is the product of probabilities. To solve this, I transformed its age probability using negative logarithm. As you can see here, that changes the product maximization problem and into a sum minimization problem. After that transformation, I can apply the algorithm normally. Then I reconstruct the path, convert the result back into final probability. This is a nice example of adapting a setting standard shortest path algorithm to a probabilistic setting. Now here. Six. D I J Uh, this prints the safest path and the final path safety probability. I transform possibilities using negative logarithm and then apply the zigzags. Now for the final questions. Uh, Edmonds curve maximum flow. The last part is maximum flow using Edmonds curve algorithm. Edmonds curve is BFS best implementation of fault falcation. The idea is to repeatedly find an augmenting path from source to sink into residual graph, then push as much as flow as possible through that path. Every augmentation After every augmentation, the residual capacities are routed. This process continues until no more augmenting path can be found. In my implementation, I also print the augmenting path and the final maximum flow value. So this question demonstrates network flow, residual graphs, and BFS based pathfinding. And also 6 slides. Sorry. This prints the augmenting path and the final maximum flow. The algorithm uses BFS on the residual graph. Uh, to conclude, this coursework helped me apply many important concepts from data structure algorithm in Java. Across the project, I used recursion, dynamic programming, greedy methods, graph algorithms, memorization, multi-threading, and GUI design. I also learned how to compare different approaches such as historic versus brute force and sequential versus parallel execution. Thank you for watching my video.